All right, let's talk about this equation which relates pressure and volume in adiabatic processes. This formula is only for adiabatic processes, meaning processes where, for example, the pressure and volume might be changing, but there is no transfer of heat. Now, if there's no transfer of heat, that means that something else must be causing the change in pressure or volume. For example, if I have a piston, and inside that piston I have some gas. Now, if I were to increase the temperature of this gas by adding heat to it, right, then obviously the temperature will increase and the pressure will increase at constant volume. But I'm going to do all this without adding heat because I have an adiabatic process. So let's imagine right now the initial pressure is 100 kilopascals, the initial volume is 40 centimeters cubed, and then I compress the gas. So I'm doing work on the gas. Now, if I do work on the gas, I'm adding energy to the system. And because I add energy to the system, some things are going to change. The temperature here will increase. I do this quickly. I do this quickly enough that heat doesn't have a chance to escape the environment, and so therefore the temperature increases. But also what's going to happen here, as the volume decreases, is the pressure is also going to increase. So as I said, this is an adiabatic process, meaning that the heat transfer is zero, and therefore the change in internal energy in this gas will equal to whatever work I do on the gas. So let's say this new volume is 10 centimeters cubed. So I essentially quartered the volume. What will my new pressure be? So this is a situation where I use this formula on the left. So remember that to say that P1 V1 to the power of 5 over 3, and that 5 over 3 is on the V1 only, okay? That means that no matter what values P1 and V1 are, they will always equal to the same number. To say that they're equal to a constant means, for example, if I change something like P2, and therefore that causes a change in V2, or I change V2, like in this case I've changed the volume by compressing it, and that has resulted in a change in the pressure, giving me a pressure of P2. Still, when I multiply this number by this number to the power of 5 over 3, I'm going to get the same number that I would have when I multiplied them in this case with my original pressure and volume. That's what it means to say that that function equals to a constant. And so this is a really useful thing in physics, this concept, this principle of saying something equals to a constant, therefore A1 times B1 is equal to A2 times B2. That's a really common concept that we use to solve problems in physics, so you need to be very familiar with that. All right, so let's fill in my values here. So I'm going to convert my pressure to pascals. It's 100 kilopascals, so 100 by 10 to the power of 3 times my volume. What's my volume? Again, I want to convert all these things into SI units. Now, some people will say, well, the centimeters cubes will cancel here and there anyway, but I always convert everything to SI units. That ensures that my answer will be in SI units, and it prevents me from making any mistakes along the way. So 40 centimeters cubed, you have to remember that the brackets here is around the entire, and that bracket should really be, in here. So it's on the entire thing here, the cubed. And so that means that a centimeter is 10 to the power of minus 2 meters, and all of that is cubed. So again, this is just practicing that use of prefixes and how to work with prefixes when we square them or cube them. And so that gives me, using my power rules, 40 by 10 to the power of minus 6. I have minus 2 times 3. That gives me 10 to the power of minus 6 meters cubed. So now it's my meter that is being cubed, and this is all bracketed here, if you like. Okay. So I fill in that value, and don't forget that we have to raise that to the power of 5 over 3. Then that is going to equal to, well, P2 I don't know yet, times my V2 volume, I do know that. Again, converting to meters cubed, I'll get 10 by 10 to the power of minus 6 raised to the power of 5 over 3. So at this point, if you're working along with me, I suggest you pause the video and try to solve this by yourself, making sure that you're using your calculator carefully to come up with the right answer. Okay, so hopefully you've come up with an answer, and hopefully I've been careful enough with my calculator. So on the left hand side, I'm getting this. on the right hand side, when I raise this volume to the power of 5 over 3, I get this. And then I just rearrange my formula to get P2 on its own, so I find that P2 is equal to this. And I want to express this in kilopascals, let's say. So that's going to give me an answer of approximately 1000 kilopascals. So hopefully you got the same answer. Okay, you don't need to be able to derive this formula. This formula is given to you, and the derivation is complicated. You know, anybody who wants to know the derivation, there is a separate video on that. But it's not something that you need to be able to do, and it involves a lot of integration and other calculus. So not needed, interesting. But what you might need to be able to do is to use this formula to derive another formula. This topic used to be on a separate section of the IB course. It was part of an option that you didn't have to do, the engineering option, and they've moved it into the core part of the course. And one of the things that used to be on the option, which may or may not be part of this new syllabus, but it's worth knowing, is the derivation of the following formula. So we want to use this formula to prove that actually T times V to the 2 over 3 is equal to a constant. So how do we do that? Well, we start off with our initial formula, and again, knowing what that means that no matter what I do with P1 and V1, if I change those values, I'll still get the same number when I multiply them together. And so I start with this, and I also know another formula that relates pressure and volume, my ideal gas equation, so I know that PV is equal to N or T. Now, I'm going to rearrange that into this form, PV over T is equal to NR, because N is the number of moles and R is the universal gas constant. So assuming the amount of gas stays constant, then N times R is also a constant. So I'm just going to say PV over T is equal to K. Now be aware that this K value and this K value are not the same thing, they're not the same number, okay? I've used K in both cases just because we just use K as a general constant, right, to mean a constant value. They're not actually the same constant though, and you should be aware of that. Okay, so again, I'm going to do the same thing that I do with my other formula. I'm just going to express it in this form, which is really useful. And then I'm basically going to divide both equations. Okay, so I can do that. If I have this is equal to this, and this other thing is equal to this, then the first thing divided by the second thing is equal to the other first thing divided by the other second thing. In other words, if I have that A is equal to B and C is equal to D, I can automatically say that A over C is equal to B over D. If you don't believe me, fill in some numbers and you'll see that it is correct. Okay, so dividing both equations, I get this. And now we're going to try and clean this whole thing up. So, first of all, my P's all cancel, so that's easy. And I'm going to move over to the side to clean the rest of this up. So I'm just going to take this section here and show you how we can tidy this up. And I suggest you pause the video and you actually practice through this yourself and see if you can get the same thing as me. So pause the video now and try that. Okay, so we're going to take this, and I'm going to take the principle that if you have something divided by a fraction, that's the same thing as something multiplied by the inverse of that fraction. So I'm just going to take this and multiply it by T1 over V1. So I flip my fraction upside down and I multiply it instead of dividing. And that's a rule in maths. I hope you're familiar with that. If you're not, now you are. Alright, so from here, again, we continue to tidy this up. We get this. And then we get this. And you say, well, I'm just after writing the same thing again, right? Well, that's because what I'm going to do is I'm going to add a 1 here. V1 to the power of 1. Why am I doing that? Because 1, I can rewrite that as 3 over 3. Okay? And I'm going to do that so that I can tidy up my powers here. Because I have V1 to the power of 5 over 3 divided by V1. So how do I tidy that up? Well, the easiest way is if I get them both raised to a power, and since the power is a fraction, I want them to both have the same denominator, so I can tidy them up. Again, I'll show you that in a second. So for now, this is our sort of simplified, cleaned up version of this formula. Okay, and then again, working to the side, well, V1 to the power of 5 over 3 divided by V1 to the 3 over 3, again, using my maths rules, I can bring this V1 to the power of 3 over 3 from the bottom to the top as long as I change the sign on the power, which is what I've done. And now I just use my power rules, and I get that V1 to the power of 2 over 3. Okay, so that's all tidied up, and I'm just going to do that for both sides of the equation here. And now I have my proof. Because to say that T1 times V1 to the power of 2 over 3 is equal to T2 times V2 to the power of 2 over 3 is to say that T times V to the power of 2 over 3 is a constant. So that's a little proof there that's worth knowing in case the question asks you to either A, prove that using the adiabatic PV formula, or maybe to solve some problem involving temperature and volume. May not be necessary, but good to know how to do.